All right, so this is actually the last lesson in the entire course on the functions unit. And coming back to some of the ideas of exponential and power functions, but looking at it in a different way. And maybe I'll even start with this graph, which is extremely pixelated. This is actually showing you the graph of y equals 2 to the power of x, a fairly simple exponential function. But it appears like a line because if you have amazingly good vision for this pixelated screen, my y-axis is not going up by a linear amount. It's going up by powers of 10. That's 0.1, that's 1, that's 10, 100, 1,000, 10,000, and so on. And when you have the scales of certain functions going in by orders of magnitude, we say, then you can make an exponential function, in this case, look linear. With that said, how do we use this? Well, here I have some function, and it looks like a linear function. And if I look at this linear function, it appears to have a slope of 1/2 and a y-intercept of -3. So 1/2 x minus 3. And if this, for a line, that is the equation, or one possible equation for this line. However, if I look at the writing here, this is what we call, I'm saying this is a semi-log function, where all the y values, the natural logarithm has been taken of them, which really means all these y values here we see are not y, they're the natural logarithm of y. So my equation is actually easy to adjust. My equation, instead of y equals 1/2 x minus 3, is actually the natural logarithm of y equals 1/2 x minus 3. And so let me write that down. And so the natural logarithm of y equals 1/2 x minus 3. All right, so that's actually what this is showing. If every y value the natural logarithm has been taken from it. Well, I can write this using what we've learned about logarithm laws and exponential, rules of exponents. I can write it as a power function. As an exponential function in the form a times b to the power of x, where b is the base of this exponential function. How can I do that? Well, if I look here, first thing I want to do is write this in exponential form. This is in logarithmic form. And remember that ln of y means the natural logarithm, or log base e of y. So writing this in exponential form, this is e to the power of 1/2 x minus 3 equals y. All right, what can I do with that? Well, I'm just going to write the y first to be kind of boring. And I'm going to look at this part here and realize I want to do two things with this. 1/2 times x, that's the same as e to the 1/2 to the power of x. And take away 3, that's the same as multiplying by e to the -3. So everything you see highlighted there, I can see from right here. And sometimes it's more obvious if you look at it backwards. 1/2 times x is 1/2 x, and we multiply two powers of the same base, we add our exponents. So 1/2 x minus 3 is what I see there. All right, if I do that, then if that e to the -3 is a constant, I'm going to write that first. I get e to the -3 times, right here, I'm just going to write this as e to the power of 1/2 all to the x. Keep in mind, e to the -3 is a constant, and so is e to the 1/2. And that e to the 1/2 is my constant base. And so I now want to evaluate these to three significant figures. And for e to the -3, I get approximately 0.0498. And for e to the 1/2, I get approximately 1.65. And that 1.65 is being raised to the power of x. And notice what I have now is an exponential function where 0.0498 is the coefficient, 1.95 is the base of the power of x. And so I have taken a linearized version of this exponential function in which all my y values had the natural logarithm taken of it to make it appear like a line. And in doing so, I was able to come up with what appears to be a rather complex exponential function without using regression or anything beyond a scientific calculator. So for the second part, I want to imagine if this is a log-log function, which means the logarithm has been taken of both the x and the y values. And which means for this equation, I want to imagine it not just being the ln of y, it's also the ln of x. So that equation will now look like this. So the ln of y equals 1/2 the ln of x take away 3. Now, any equation in this form can be written as a power function. And a power function looks like this, where my variable is the base, and the base is being raised to some power, and a is the coefficient of it. Same idea, though. To get into that form, I need to use my logarithm and exponential laws. First thing I want to do here is write this in exponential form. And so similar to before, I can write this as e, I don't know why that's purple though, e to the power of 1/2 ln of x take away 3. All that must equal y. All right, what can I do next? Well, first, I'm going to break this here up into two parts. I'm going to write this as, I'll put my y first. Y equals e to the 1/2 ln of x times e to the -3. We saw something similar in the last question. Right, and if you look backwards, perhaps it gets more obvious. That e to the -3, we've seen that before. That's a constant. I'm going to write that first. E to the -3 times e. And this time, that if I look at the 1/2 ln x, that 1/2 is a coefficient of a logarithm. Remember, any coefficient of a logarithm, we can use a logarithm law and rewrite it as a power of the input of the x in this case. So I can rewrite this as e to the power of the natural logarithm of x to the power of 1/2. And now, if I look at this part right here, I have an exponential function of base e, and right away inside it, I have the natural logarithm, which is the inverse of an exponential function of base e. So as we've seen before, those cancel each other out, so they're inverses of one another. And that leads me to e to the -3 times just x to the 1/2, which notice is, again, a power function. That e to the -3, I saw that in the last question, that we already evaluated to be approximately 0.0498. So I'll kind of finish this right here. So I can say y is approximately 0.0498 times x to the 1/2. And again, like before, I was able to come up with a pretty complex equation without using any regression, using really our understanding of logarithms and exponential functions. All right, and so in general, there's two types of these functions we look at, and that's what's kind of summarized up here. Either where just one of the variables, either the x or the y, has had a logarithm taking of it, that's a semi-log model, or both the x and the y. And again, the most recent example I went through is what we call a log-log model. All right, the rest of this is all about this data comparing the distance of planets from the sun with its orbit in days. And I have this table here in which the distance is all in millions and the orbits are all in days. And the first thing I want to do is use regression technology to come up with a power function to approximate this. And this takes a little bit of time on a graphing calculator, but essentially I want to make a table in which all my first column will be these values, all my second column will be these values, and I want to go to power regression. You want to be familiar with your particulars of your GDC, but pretty quickly, once you type in this table, you should be able to get a power function, and to three significant figures, it should be about 0.201 times x to the 1.50. And that's using regression. And again, any power function can be written in this form. A coefficient, x to the power of some number. All right, what I want to do now, though, is show how we can actually come up with virtually the same function without using any regression technology. But first, I want to find a log-log model of this. I want to find the natural logarithm of both the distance column and the orbit column. And this takes a little bit of time, and it's a little bit tedious, but I want to find the natural logarithm of all these numbers. And I'll start to write these in all to three significant figures. But for example, that 4.06, maybe I'll zoom out, that is simply just 57.9 after I find the natural logarithm of it. And I'm going to do that to all of these. So you can now just watch in excitement as I write down a bunch of numbers. Pretty exciting to watch. This is all how I'm trying to build up my YouTube viewing hours. Just me writing down numbers. All right. Oh, okay. Again, a bit tedious, but not difficult. So if I were to make a scatter plot of this would form a clear linear function. It would be, and I could use a graphing device to plot this information into a table and come up with a linear model that way. And the correlation coefficient would be extremely close to 1. However, I'm just going to come up with a linear model by finding the slope of these, in which I'm going to take the last point and the first point and find the slope between those. And so I can do that quite quickly. And so my slope of this linearized model is going to be 11.4 minus 4.48 in my numerator and 8.68 minus 4.06 in the denominator. And keep in mind, all of these values were rounded to 3 significant figures, so everything here is an approximation. But I get it really close to 1.5. So there's my slope of this linearized function. And if I want to find the equation of any line, I just need a slope and a point. I got lots of points. I'm going to use that first point, 4.06 for my x and 4.48 for my y, and use this slope point form or gradient point form of the linear function, y equals m times x minus x1 plus y1. I'm going to use this, which my slope is approximately 1.5, x minus some point. Again, I'm going to use the first point from the table, 4.06 plus 4.48. Keep in mind, this is my linearized equation, all right? So I'm ignoring the fact for a moment that I actually found the ln of x and the ln of y to get these values. Distribute the 1.5 and clean this up. Pretty quickly, I get to 1.5x minus 1.61. All right, that, keep in mind, is a linear function that models this data here. But this data here is actually not x and y, it's the ln of x and the ln of y. So to be a little more accurate, I really now should say the ln of y equals 1.5 times the ln of x minus 1.61. All right, and now, like we did in a previous example from these notes, I want to turn this into a power function. And so it's virtually identical in process to what I did right here for this question. So I'll do the same sort of idea. I'll put this in exponential form. I get e to the 1.5 times the ln of x minus 1.61 equals y. I'm going to write this as e to the negative 1.61 times e to the 1.5 times the ln of x. And again, I'm just taking these parts here and breaking them up into two separate powers being multiplied to each other and putting the e to the power of negative 1.61 first because it is a constant. And again, that 1.5 being multiplied to the natural logarithm, I can rewrite using a logarithm law. So I get e to the negative 1.61 times e to the natural logarithm of x to the 1.5. And like before, those are inverses of one another. And so what do I have left? I have y equals e to the negative 1.61 times x to the 1.5. And as what I hope comes as no surprise, if I decimalize e to the negative 1.61, I get approximately 0.2 times x to the 1.5. And if you look at this, keep in mind this equation, I came up without using any regression technology, is nearly identical to what I had right here, which was using the regression equation or regression feature on my GDC. And that's it for functions in this course.